Thanks for watching AI Weekly Update from Henry AI Labs. Chip placement with reinforcement learning is a huge step forward in optimizing hardware for different algorithms. This paper uses graph convolutional networks to facilitate the netlist input representation to Q-learning for chip placement. This algorithm is really fast, designing chips in 6 hours that would take experts several weeks to do manually. Supervised contrastive learning leverages the success of positive-negative contrastive learning to achieve up to a 2.8% gain on ImageNet Top 1 with the ResNet 200 model. This adapts contrastive learning by using all images from the same class as positive keys and images from other classes as the negative keys. Hugging Face launched their YouTube channel with a really comprehensive talk about the future of NLP from Thomas Wolfe. This talk covers an enormous range of topics in NLP, such as model compression, scaling language models, generalization, and more. Experience Grounds Language is a really interesting paper about how language needs to be grounded in order to have meaning. This paper describes 5 levels of world scopes that build on each other to achieve language understanding. Carefully curated corpuses such as Penn Tree Bank into internet-scale data, multimodal combinations where language makes sense of other inputs such as vision, embodiment, and social interaction. The ingredients of real-world robotic reinforcement learning gives a great explanation about real-world challenges such as the inability to reset the environment to the initial state, high-dimensional input observations, and reward inference. Towards robots that can learn on the fly introduces a relatively simple approach to adapt robots trained on 600,000 grasping attempts to new environments such as novel objects, lighting configurations, or grippers. Adversarial Latent Autoencoders achieves amazing disentanglement in facial image generation by integrating advances from StyleGAN into the adversarial autoencoder framework. Quant Noise is a new model compression algorithm from researchers at Facebook AI that can reduce model size from 10 to 20 times without losing performance and up to 50 times with some performance loss. This includes reducing Roberta from 480 megabytes to 14 megabytes. This is done by applying quantization-aware training to a random subset of the weights rather than the entire network. ResNet is a novel ResNet design that shows that manual design of image classification networks is still ahead of neural architecture search algorithms for the time being. Automating data augmentation is a nice overview of the challenges in image data augmentation, such as moving from going from manual to automated search, gaining a theoretical understanding of why augmentation is successful, and using augmentation to fix problems in the model, mostly caused by class imbalance. Specification Gaming describes the same idea as the surprising creativity of digital evolution, further providing a list of examples where AI has gamed the system and found an undesirable solution by exploiting a poorly defined reward. Analyzing reinforcement learning benchmarks with random weights is an interesting idea to gauge the challenge of different reinforcement learning challenges. Pieboy is a new interface to play games such as Mario and Pokemon through Python. The ICLR conference has kicked off with a lot of really interesting talks and paper summaries posted on Slides Live. In this week's episode of Machine Learning Street Talk, Tim Scarf, Yana Kilcher, and I will be reacting to Thomas Wolfe's The Future of NLP on their new Hugging Face YouTube channel, covering a ton of different topics in natural language processing. We'll also be interviewing Jonathan Frankel, the author of the Lottery Ticket Hypothesis, one of the most exciting papers in deep learning and artificial intelligence. Jonathan is also the author of Linear Mode Connectivity and the Lottery Ticket Hypothesis, Training Batch Norm and Only Batch Norm, Comparing Rewinding and Fine-Tuning and Neural Network Pruning, amongst others. Please leave a comment with any questions you'd like us to ask Jonathan in this week's episodes of Machine Learning Street Talk. Chip placement with deep reinforcement learning is a really exciting result from Google AI that generates chip placements in under 6 hours, where it takes human experts several weeks to do this, additionally improving on chip placement metrics such as wire length and congestion. This is the latest work since Jeff Dean's paper, The Deep Learning Revolution and its Implications for Computer Architecture and Chip Design, as well as his keynote talk at ISSCC 2020, which was recently posted on YouTube as well. So we're imagining optimizing these chips for running inference and training of these different deep neural network models, and not only manually optimizing these chips, but using machine learning and reinforcement learning to optimize the design of the chips that then run the machine learning models on them for different applications like question answering or image classification. So this paper is talking about customized chips for different neural network models. Compare the BERT architecture with a ResNet. They each have these different architectures like the query key value network, the transformer self-attention layer, compared to the ResNet skip layer, convolution, and these different operations could benefit from not only having an optimized layer distribution for the same kind of general CPU plus say 4 GPU computing cluster setup, but from further having optimized chip placements within something like a Google TPU pod for each different model. So a different optimization for the BERT model's inference compared to a ResNet. So this paper is a really impressive use of reinforcement learning for combinatorial optimization. You can see this comparison of 10 to the 9,000 possible chip designs compared to 10 to the 360 for Go or 10 to the 123 for chess. So AlphaGo and more recently Mu0 that solve these combinatorial spaces have been really successful with using ResNet to form the input representation mapping from high-dimensional image-like game boards into lower-dimensional state representations that can be used for reinforcement learning. So a similar success as in like computer vision or these different control models. So chip placement with deep reinforcement learning is going to use a graph convolutional network to reason about the input state, which is the chip netlist in this adjacency matrix, which is reasoning about the different nodes on the board, the metadata about the nodes, and then their locations relative to each other. The authors initialized a network with 10,000 manual chip placements and used this to train the value network with supervised learning. This helps the reinforcement learning model begin to get a sense of how to map from this high-dimensional state representation, where it's using the graph convolutional network and metadata about the nodes, to map that into a lower dimensional representation that can be used for something like Q-learning to place future nodes on the board. This plot shows the benefits of pre-training for the policy in this way, and this plot shows the gains on transfer learning to novel chip designs and how this works with respect to that input dataset size. There's been a lot of interest in contrastive learning lately. These algorithms learn representations by making them similar to positive examples and dissimilar to negative ones. This idea that you learn a representation such that you can tell objects apart from one another. In a lot of recent papers like Curl, Momentum Contrast, or SimCLR, the positive examples are data augmentation transformations of the same image, and the negative examples are all the other images in the queue or mini batch. Learning representations by maximizing similarity between augmented views of the same image has been really successful, and it's reaching new heights in reinforcement learning control and unsupervised representation learning. Supervised contrastive learning brings the contrastive loss function into supervised learning by maximizing similarity in the embedding space between images of the same class. So instead of having only one positive key, which is an augmented view of that same image, all the images from the class are used as positive keys. So you put the embeddings of all the dogs closer than the cats or trucks or ships or frogs or something like that. This works with a two-stage pipeline where the model is pre-trained with the contrastive loss and then fine-tuned for classification by replacing the top layer and then training a new layer with the cross-entropy loss function. The authors show 1.8% ImageNet top 1 gain with the ResNet 50 and 2.8% with the ResNet 200. They also show that this makes it more robust to corrupted images, evaluating it on the ImageNet C dataset. On a side note, I think it's cool to see the increased use of this ImageNet C dataset and discussion in NLP papers about testing models on hard or adversarial corrupted datasets. The authors further show that the supervised contrastive loss function is more robust to augmentation and optimizer hyperparameters, but has about the same sensitivity to the learning rate hyperparameters. They further show an analysis of the gradient to show that this algorithm learns more from hard examples, such as the embedding distance between a golden retriever and, say, a French bulldog versus another view of a golden retriever. Hugging Face, the open source Transformers library, has recently launched their YouTube channel with a really great talk from Thomas Wolfe about the future of NLP. This talk covers a massive range of topics in natural language processing. This slide gives the high-level overview: model size and computational efficiency, talking about pruning, distillation, quantization papers, compression algorithms such as their distill-BERT model that looking at making more efficient transformer models and compressing these pre-trained models. The talk then goes on to making use of more data and reviewing OpenAI's paper Scaling Laws for Neural Language Models, further discussing the idea of a phase shift where we see qualitatively different behavior in these language models as they get larger and get more data to train on. The talk further describes problems with generalization, such as birds of a feather do not generalize together, showing that BERT models trained on the same in-domain data will generalize differently to out-of-domain data. The talk also describes the text-to-text formulation of NLP tasks used in Google's T5 model, as well as Facebook's BART. Text-to-text input-output formulations to unify all NLP tasks, such as the natural language processing decathlon, is an idea that I personally think is really interesting. This was a really awesome debut for Hugging Face's YouTube channel with a ton of different topics in NLP covered. If you're interested in these topics, please stay tuned to Machine Learning Street Talk, where Tim Scarf, Yannick Kilcher, and I will be reacting and commenting on this presentation. Another really interesting paper that came out this week is Experience Grounds Language. This is this idea of having language that represents meaning embodied in some kind of world, this idea of embodied cognition. So this paper describes 5 different levels of world scope. So it starts off with corpus. things like the Penn tree bank dataset that are carefully manually curated to have this kind of structure in the dataset that the natural language processing model can learn from. The second level of world scope is the internet. The internet is these ideas like how GPT-2 is trained on all the articles that are scraped from the internet and then passed through that Reddit filter. The internet is now, instead of having these carefully curated data sets, we just have like all the text that's ever been written and that kind of massive scale of just text data. But then the third world scope is about perception, where language has to describe some kind of physical world. So this is the idea of models like ImageBERT or VilBERT, where you have this multimodal alignment between text and then vision, or you can imagine text and audio, or all kinds of different things. There's another interesting thing like the Open Street View dataset from Google, where you have this street view and you're navigating, and you use natural language in order to make sense of the visual world. Other things like AI2's RoboThor, the point scale navigation, all these different kind of combining visual worlds and visual like state representations with natural language so that the language is grounded in some world scope. The fourth idea is embodiment, and the fifth is social. So these different ways of using language to make sense of some world. I'm not exactly sure what embodiment means, but social meaning maybe like how you interact with other agents in the environment as you're sensing all these different like input representations. So it's a really interesting paper, a great read on this idea of embodied cognition and how experience grounds language and gives language meaning. The Ingredients of World Robot Reinforcement Learning from researchers at UC Berkeley is a really interesting paper about some of the different factors that make it really hard to do real-world robotic control learned through reinforcement learning compared to these simulated environments like the OpenAI Gym or say the DeepMind Control Suite. So the first point they list in their paper is that there's no reset mechanism in the real world. So in these simulations, we learn from these episodic trajectories where you start from an initial state and then you have a go at the task and then you're reset back to that initial state. But say you're a robot that's trying to learn how to pick up a cup on a table, but you accidentally push the cup off of the table. There's not, like the robot doesn't know how to go and grab the cup off of the floor and put it back on the table. And even if it pushed it like farther on the table, it doesn't know how to reset it to the initial state. So what you'd have to do in the real world is build all this infrastructure around it to push the cup back to the original state and then reset the episode, or have a human intervene and put the cup back to the initial state. So that's the first challenge of real-world robotic learning, is that there's no reset mechanism, no just reset to the initial state for sampling these trajectories and episodes to learn control tasks from. The second point they list is that they have to take these observations from these pixel representations. They don't have all these meta information that you get in things like OpenAI Gym, where you have things like the angular velocity on the hip and knee joints and something like the bipedal walking agent. So they have to learn to map from this high dimensional representation into lower dimensional representations that can be used for reinforcement learning. And another component about that makes it so tricky is the state might not be Markovian. Markovian is this idea that all you need to predict the future is contained in the current state, and that might not be the case with these pixel inputs. The third point they list is that there's no reward function. You need to train these vision models that can tell when the robot has reached the goal. So you can't just, if it picks up the cup, it doesn't just know that it's picked up the cup, and it's hard to construct some way of telling it that it successfully completed some kind of task, like stacking blocks on top of each other or sorting objects into different bins. So you need to have this auxiliary mechanisms or infrastructure to give the robot the reward function. So they come up with this algorithm, the reset free learning learned perturbation controller, which helps the robot overcome these problems of reset free learning, learning from sensor informations or high dimensional observations that might not be Markovian, and then reward inference. Towards learning robots which can adapt on the fly is about how you take a pre-trained policy and adapt to new things like different parameters on the controller, different types of objects, different lighting, and these different physical conditions that could be put onto the robot that make this new task harder. So this paper is talking about an algorithm to go from a model that's pre-trained on about 580 or 600,000 different grasping attempts. This is follow-on work from the QT-OP paper, which is like this arm farm of robots that just try to do the grasping task over and over again, and then all the experience is saved up and stored in this data set that can be used for offline reinforcement learning. So they're talking about how do you go from that model that's been pre-trained on an enormous amount of grasping attempts, 580,000, or I think it's 608,000, and then how do you pre-train that, and how do you fine-tune that onto a new kind of object or a different kind of gripper? So say you move the gripper 10 centimeters to the right, or you change like the lighting conditions in the environment. So their approach in this paper is to just go into the new environment, explore, get like 800 grasping attempts, and then just integrate that into the previous data set with the 50% sampling ratio. So even though you have 800 attempts in this new environment and then this previous data set of like 608,000 different grasp attempts, you still are going to do 50% in the batch of the previous data and then 50% of the new data. And they show that this actually works surprisingly well, going from 86% to 43% when you shift to this new environment. And then when you do this fine tuning, it goes up to 98% success. And they show that you can just, in like a continual learning way, you can just iteratively do this with new tasks, going from harsh lighting, where you're doing the 50% data blending of the harsh lighting and the previous data, then transparent bottles, which is this notoriously hard task where it's the see-through bottles and the vision systems really have a hard time with this. Then the checkerboard backing, the extended gripper, changing the gripper, and the offset gripper. So showing that you can do this continual fine tuning, and the robots adapt pretty well with this new algorithm of mixing the data batches and then fine tuning in that way. Adversarial latent autoencoders is the latest kind of generative model that has a really remarkable ability to do disentanglement representation learning, where for example you have a face image and you just change the hair or just put sunglasses on without like changing the entire image. So you can isolate these different like factors of variation and just change like them slightly. So you're just changing like whether the facial expression is smiling or frowning without moving the rest of the image too much. So they do this by combining the power of these autoencoders and the generative adversarial network formulation. So you use the adversarial loss from the GAN to make the images more realistic and rely on that natural image manifold, but then you use the power of the autoencoder to do disentangled representation learning. And then the new idea here is that instead of having something like a variational autoencoder where you penalize the compressed representation by doing the KL divergence with some priorly defined probability distribution like a Gaussian or something like that, and comparing the two probability distributions, you're comparing the divergence between the encoded representation as it goes from the latent space into this intermediate mapping space W. So in the exact same way that the StyleGAN2 model uses this W mapping network to have more factors of variation by going from this original space Z into W and then putting W into the intermediate feature maps of the generator through these adaptive instance normalization layers, you're doing this kind of intermediate latent space that facilitates with disentanglement and having these high quality models. Quant Noise is a compression algorithm from researchers at Facebook AI that can reduce model size by 10 to 20 times without loss of performance and up to 50 times with some loss in performance. This involves having a Roberta model that takes 480 megabytes to store and reducing it into 14 megabytes. This is done through a variation of quantization-aware training. Quantization is this idea that instead of having like 32-bit floating points to store the weights, you quantize them and map them such that you can store the weights with 8 bits or 4 bits. But the previous way of doing this, just taking the 32 bits and going to 8 bits, is going to have some kind of performance loss. So one way of alleviating this is quantization-aware training, where randomly you will do this discretization operation during training and then do the straight-through estimator to put the gradients through the mapping from 32 bits to 8 bits. But this idea of quant noise is instead of doing quantization-aware training on the entire weight set, you're going to do it on a random subset, such that the noise from the straight-through estimator going through the discretization doesn't cause too much instability during training and performance loss. So it's a really interesting new algorithm. More and more is being developed around quantization. It's implemented in PyTorch and TensorFlow. You can use it easily to get compressed models that don't lose too much performance. ResNet split attention networks is the latest modification to the ResNet architecture that improves performance up to 81.13% top one ImageNet accuracy with the similar computational complexity as a ResNet 50 model. So they're doing this by introducing this new split attention mechanism, kind of this variation of going from group convolution in the ResNext, and then we have these split attention blocks like SCNet and all of these different ways of grouping it and doing the different attention on the intermediate channels within these ResNet blocks. But what I think is really interesting with this paper is that it's showing that manually designed architectures really aren't lagging too far behind neural architecture search. Although neural architecture search is really interesting, and there's a lot of cool papers, particularly coming out of that Google AI lab with Quackly, with the evolving normalization activation layers, AutoML0, and the swish activation function, but the manual design is still really on pace. The ResNet model is performing better than these models like EfficientNet that have been found with this exhaustive and computationally intense neural architecture search. So although neural architecture search and AutoML is really exciting, it's not quite reached its potential of surpassing human design architectures. So you can see the model for the ResNet block, this split attention layer, and kind of imagine that it would be hard to parameterize such a space that a neural architecture search could find something like this. Automating data augmentation, practice, theory, and new direction is a great overview of recent efforts in the data augmentation for image data space. The first part of the survey describes the different challenges in data augmentation, from manual to automated search, from practical and empirical benefits, from a theoretical understanding of why these rotations and geometric flips are giving the models a better decision boundary and a better sense of the images, and then from coarse grain to fine grain model quality assurance. So the first algorithm to describe is this TANDA algorithm, Transformation Adversarial Networks for Data Augmentation, where they have this way of you take an original image, then you apply a sequence of transformations to it, and then the discriminator tells whether it's a real data point or an augmented data point. So a cool way of making sure that the augmentation doesn't corrupt the image too much. So say you have the MNIST data set where you have the different 1, 2, 3, 4, 5, and if you horizontally flip it and rotate it, it's not really a 6 anymore. So I think it's a cool algorithm of making sure that these sequences of geometric transformations or whatever transformation is going to augment the data point doesn't ruin the label of it. So it's no longer a 9 or something like that. So the blog post then compares this with AutoAugment and the automated search algorithms like RandAugment. And then it furtherly goes into this idea of how can we theoretically understand data augmentation, and then looking at particularly using data augmentation for model patching. So another similar idea with this paper, DermGAN, where they use the pix-to-pix model to increase the diversity and alleviate class imbalance in the data set, is this idea of trying to make, when you have these particular modes that commonly arise because of class imbalance, you can use these data augmentations to try to fix that problem. Specification Gaming, the flip side of AI ingenuity, is a similar article as The Surprising Creativity of Digital Evolution, where they show how evolutionary algorithms and these different algorithms can exploit flaws in the design of the game in order to achieve the reward. So that example of where it's like a boat racer going through an obstacle course, and there are intermediate gold coins to collect that respawn. So the robot, the agent, instead of going through the course, just circles around the gold coins and maximizes the reward that way. So there's this list. They have this Google Sheets list of all these different cases of where they define an objective like hide and seek or Lego stacking or football, and the agent comes up with some clever way to just exploit the way the game was defined. But something that's interesting about this article compared to The Surprising Creativity of Digital Evolution is that they describe this difference between undesirable solutions like flipping a Lego block in order to get the max height reward instead of stacking it on other blocks, and then compare it to a desirable novel solution like the Move 37 in the AlphaGo algorithm, where it has this unexpected solution, but it actually is good in that case. So I think it's an interesting discussion of not being too constrained in the system, but then also not having it so it just exploits the definition of the game. Analyzing reinforcement learning benchmarks with random weight guessing is an interesting idea to benchmark the challenge of different reinforcement learning tasks. So comparing the difficulty of cart pole balancing with, say, the bipedal walking agent by having all these different random weights for the controller network, and then looking at the distribution of the rewards achieved in each of these tasks with respect to these random weights. So I think it's an interesting way to think about these reinforcement learning benchmarks. It's kind of interesting. I mean, you can't imagine that something like that could really do DeepMind Control Suite. You could have just random weights that would be able to do cheetah run. But for simpler tasks like cart pole balancing and bipedal walking, I think it's a really interesting idea. Pieboy is a really cool interface for the Game Boy games like Mario and Pokemon in Python that can be interfaced with these reinforcement learning algorithms. I'm really excited to see what kind of algorithms work with the Pokemon game and how challenging that kind of a task is. The ICLR conference is beginning, and a lot of these talks are already available from the workshops that you can view on Slides Live. There's a lot of really cool stuff, such as Jeff Kloon's latest talk on the Learning to Continually Learn paper and AI generating algorithms.